family person health issues. And it's very nice to talk after Professor Shan, Professor Alisha, and then Professor Gupta. They have very senior and they have done tremendous work in their respective field. Uh, Professor Gupta has a lot of work in the real time, like what the membrane fouling, scaling, all those things happen. So it's always nice to hear their talk. Similarly for Professor Sean and Professor Alisha. So today I'm going to talk on fabrication of electroconductive membranes, which my research group is for last couple of years. And even when I was doing my postdoc, I have started that work in Ben Gurion University of the Negev in Israel, Beersheba, where we have tried to come up with a new material called laser-induced graphene to fabricate these new generation of these membranes. So quickly, I will give an overview what right now we are doing at our lab in IIT Bombay, which I named Environmental Nanotechnology Lab. And a majority of our focus is right now going for membranes for desalination and wastewater treatment, and where we are trying to deal the problem related to permittivity, selectivity trade-off, membrane fouling, how we can effectively manage brine, and also how can we reduce the cost of treatment. For that, we are trying to go with several new methodology. One is like our new generation membrane, like electroconductive membrane. We are trying to integrate these membrane technology with other processes like advanced oxidation process and other thing. We have several projects like with SIR, we are trying to develop these electroconductive surfaces, better electroconductive surfaces, which can be utilized for electroconductive membranes, deal with the biofouling. We are trying to also understand fundamentally like how like active and passive strategies to deal with these biofouling. Have developed integrated membrane technologies for industries, for industrial wastewater. Also, one ambitious project which we have taken with the ISRO to develop a water purification system based on FOMD. Apart from that, we are also actively looking for low cost materials, nanomaterials, which can be effectively utilized in membranes to come up with new generation membranes for all these problems which I have stated with that. And one of the key thing which we are also trying to see at present, like how we can deal with the emerging contaminant, especially with the pharmaceutical and personal care products at a very low concentration by using these new generation membranes. So in this talk, mainly I'm going to talk on a new material laser-induced graphene-based electroconductive surfaces, which we are trying to fabricate. So briefly, like majority of you are aware, like membrane is not new. We have started using long before, but earlier time it was not that popular because of high energy demand and lack of novel membrane materials. But especially after 1990s, we have seen a very good quality of materials as well as energy recovery units. So that's why, and along with that, strict water regulation has forced us to come up use these membrane technology. And it's also very nice if you see these membranes can give you a wide variety of treatment option. If you just take pressure driven system, we can do pre-treatment by using ultrafiltration and microfiltration membranes, and high quality of water we can get from nanofiltration and reverse osmosis. And that's why at present, if you see for membranes technology for water reuse and desalination, it's have a very high growth rate. However, if you see the major challenge, what at present the membrane technology is struggling is related to your membrane fouling, along with the colloidal organic and scaling. One of the major problem is related to biofouling, because here active microorganisms can attach with the surface, and then in presence of their if they have proper food and all, they can grow, and then ultimately they can disperse and contaminate other places in the membrane. And the whole process here, if you see depending on environmental condition, it can be happen within few hours to few days. There are several examples where the big desalination plants have need to shut down for a few within few hours to treat clean because of the biofouling. So it's showing the problem with the biofouling, and if you go with the data also, it suggests approximately 30% extra cost we are bearing because of this biofouling. Along with that, right now, if you see also, emerging contaminants also coming as a big problem for the membranes, because if we have only few contaminants, so we cannot always go for nanofiltration and reverse osmosis because they are very energy intensive process. So how just by utilizing ultrafiltration based system can we develop technology by that we can deal with these emerging contaminants. So that is also one of the key thing what we are talking. I'm going to talk, and what we are trying to develop ultrafiltration membrane, which is electroconductive. So by not giving a lot of pressure, but just applying a low voltage, we can able to remove these emerging contaminants along with the other pollutants. So for biofouling, the majority till date, or the major things what we are trying to do, we are trying to use some of the biocides, also the chlorine cleaning. But the thing is, all these strategies, like especially with the chlorine, it can also damage our membranes, especially the thin film composite membrane. So how we can deal with this problem? So if we are able to inhibit or delay these initial three steps, then we can significantly increase the life of the membrane. And for that, at present, researchers are trying to use a different strategy. For example, they can go for chemical-based modification, or they can go for a patterning, like Professor Alisha already shown, like how different kind of bio-inspired surfaces can help us to come up with a, by that we can control the biofouling. Right now in my group, what we are trying to use a graphene one by where we are trying as a both as a active as well as passive, means we are trying to come up with the texture along with if we are providing electricity or we have a composite with other nanomaterials, then it can actively also kill the microorganism. So in that, this electroconductive membrane comes into the picture, because if I'm using a graphene as a base material for fabrication of the membrane, so my surface is conductive, and we are coming with electroconductive membrane. And in if you see last few years, it has been several literatures. They have demonstrated how different kind of potential, starting from if you are using a direct current, with cathodic, with anodic, alternate current, as well as in a register mode. There are different mechanisms by that we can deal with the several problems related to the membrane technology, starting with the fouling. We can also go for fouling and wetting detections. We can improve the ion rejection as well as the contaminant removal. So, and what kind of electroconductive materials are being used to fabricate membranes? They are conductive polymer or metal-based surfaces, and also a lot of are coming with carbon-based nanomaterial like carbon nanotube and graphene. So graphene, you all aware, it's one of the 2D material. It's a sp2 hybridized, very good have a very good electrical and thermal conductivity. But if you see the traditional method, how we are getting the graphene is and if you want to fabricate surfaces from this graphene, they are mostly multi-step, lengthy and expensive. For example, if you want a single layer, it's for CVD, it's very expensive. But anyhow, for our applications, we don't want a single layer graphene. Even we are going with a solution processing, it's a multi-step process where you have a graphene oxide, then you need to reduce to the reduced graphene oxide, and then we need to have the surface or have your final membrane. So they all are multi-step process. So for that, there was a requirement of a single step process, how we can get a conductive surface in a single step. For that, this a new material which was invented in Professor Tour lab in Rice University, what they have termed as a laser induced graphene, because just by normal carbon dioxide laser, they have fabricated this surface. And it was also like other many great discoveries. It was accidental when his a postdoctoral student, Dr. Lin, was cutting a polyamide polymer. They have seen black powder, and later with a proper protocol, they have published this Nature Communication paper in 2014, where they have demonstrated how in a single step chemical free process we can get a very porous 3D graphene, having graphene surfaces. So for that, like that time I was after that, Professor Toor has contacted my postdoctoral supervisor. They had a collaboration where they tried to investigate how these laser induced graphene surfaces can be utilized in membrane technology, especially dealing with anti-biofouling properties. So in 2017 we have published like how these surfaces, they were very great anti-biofouling showing anti-biofouling properties. So when I'm talking about anti-biofouling properties, means I'm just interested whether the microorganisms are able to colonize the surface or not. But when I'm talking about antibacterial, where we are interested to kill the microorganism. So generally what we have seen, these surfaces have a very excellent anti-biofouling properties without electricity, and with electricity they can also kill the microorganisms. We have tried to understand why these surfaces has very excellent anti-biofouling properties, and we have concluded in 2018, like mainly because of these 3D textures. The texture is the main reason for anti-biofouling properties, because when we have destroyed the texture, and both like in a normal, the laser-induced graphene has a contact angle around 60-65, and we have done plasma and converted into the super hydrophilic, and then we destroyed both surfaces, the textures. And then if you see with enhanced biofouling experiments, that crust surfaces, they have shown some growth of biofilm, whereas non-crust surfaces, a normal laser-induced graphene and super hydrophilic laser-induced graphene, both had no biofilm at all. So we have concluded mainly because of these micro-sized wired and nanofibers, these surfaces have shown excellent anti-biofouling properties. Also, with the electricity, we have demonstrated it has a good antibacterial properties, and depending on 4 to 6 log removal, we can see in a batch mode, and in a flow through mode, it can even give you a better result. Within few seconds, we can see a complete inhibition. However, without electricity, what we have found is this laser-induced graphene was not toxic to microorganisms, and it was behaving like normal polymeric surfaces, where we have seen almost just less than 10% inhibition for planktonic cells, and as well as we have checked for both deposited and planktonic, and the result was all a little bit higher for deposited cell, but planktonic cell it was very less. So then the idea how now we can fabricate a laser-induced graphene-based membrane, because initially the laser-induced graphene was only fabricated on polyimide surfaces, and a majority of our water purification systems, these membranes are either from polysulfone or other kind of polymers. And then the same time from our lab and my postdoctoral supervisor lab and Professor Toor lab, they came up with a new method by defocusing as well as multiple lensing. We can fabricate these laser-induced graphene on any kind of surfaces, and that by that we have demonstrated how using a polysulfone polymer or a membrane, we can fabricate laser-induced graphene on these membranes, ultrafiltration or microfiltration membranes, and they have shown very excellent properties similar to polyimide, even better, because these polysulfone, they have sulfur, and that because of that sulfur, we have seen better electrochemical properties, electroconductive properties than the polyimide. So it has shown like how a single step we can convert these laser-induced graphene. We can convert a normal membrane to a laser-induced graphene filters. And on the basis of that, we have come up with several ultrafiltration membrane for, as you know, like we are burning the top surface with the laser. So generally, if you are taking a normal ultrafiltration or microfiltration membrane, we are burning the active layer. So it has lost its separation capability. It has very big size, micro size pores. So we have to go for a post modification if we want to have the membrane ultrafiltration or microfiltration membranes. And still it's a win-win situation because we are getting our electroconductive surface in a single steps. And we have shown with the PVA modification, with graphene oxide modification, we can come up with different, we have done different kind of pore engineering and come up with these ultrafiltration membranes, and they have shown very good properties, separation capabilities for many contaminants. However, if you see, as we have modified the surface, then we are losing the texture, and if you are losing the texture, then these surfaces are not as great for anti-biofouling property like what we have seen with normal laser-induced graphene. So still it's less than the control polysulfone membranes, but they have shown some growth of these microorganisms because of the loss of the texture. Also, recently, just this year, we also have demonstrated why the surface optimization means the when we are fabricating laser-induced graphene, then what kind of several parameters with these lasers they can be optimized if you want to have a very good quality of laser-induced graphene. Base filters for fabricating different type of interfacial evaporators or membranes, where we have demonstrated how changing even the bottom bench, like starting from aluminum, glass, or other, it can give you a different types of laser-induced graphene, and why the like image density and defocusing, how it also affect the overall properties of these laser-induced graphene. And this work came in applied material interface this year, and also these surfaces have shown very excellent interfacial evaporator properties. Also, we have used these electroconductive based membranes to remove different kind of antibiotics. And here I'm going to talk about the ciprofloxacin. We have fabricated these membranes with a PVA modification, and then we used for these for ciprofloxacin removal at different condition. Also in the synthetic wastewater at very high concentration of 10 ppm as well as 500 microgram. And in both all the cases, what we have found, it has shown very good rejection as well as the degradation. Both processes was happening together. Also, we have tried to add a persulfate activation, because these laser induced graphene, they are conductive, so persulfate activation can be also done in that. And we have tried to show like how the overall degradation can be improved. However, the rejection was very good. We are within few minutes, we are reaching up to more than 80%, 85% of rejection of these antibiotics. But along with that, there is a degradation because of electrooxidation. It's seen. So in this process, we have demonstrated like rejection as well as degradation is happening in a single step. Also, these surfaces, these laser-induced graphene surfaces, they are very excellent interfacial evaporator in presence of sunlight, and also we can use in a register mode as a Joule heater. And we have demonstrated how different kind of configuration can give us, we can design a very innovative solar stills, a new generation solar stills, which can operate both in presence of sunlight as well as in absence, and can give a very good quality of water in a very small footprint. So along with that, we are also trying to handle some of the major challenges with these electroconductive membranes. As for example, if you see, the anodic stability of these surfaces are very low. Cathodic stability is quite nice, as well as the register mode, they are working very good, but cathodic stability is not that good. For that, we have trying to improve this stability by making composite with different kind of metal and metal oxides. For example, one of the work we have demonstrated how titanium suboxide TSO composite can improve the overall anodic stability as compared to normal LIG, and they have also shown better result than normal LIG for different kind of application for virus as well as the microorganism removal. Also, like the TSO fabrication is a multi-step process, titanium suboxide. So we have what we have done, we just blend this normal polysulfone polymer with titanium oxide, and then we have done the lensing, and in a single step, we have able to convert titanium dioxide into TSO with laser-induced graphene, and they have shown equally good result like which we have shown with the normal TSO, and it was far better than normal laser-induced graphene surfaces. So in summary, in last couple of years from IIT Bombay, in last 5 years, we have demonstrated how these electroconductive membrane can be utilized and they can help us, and still we are exploring and we are trying to see the full potential and what are the major drawbacks we have and how we can improve that. We have come up with different type of ultrafiltration membranes. There are several in the pipeline, which where each time we are trying to improve their performance. They are very good to remove the viruses from the water. We have shown how it can be designed a new type of interfacial evaporator, a stacked interfacial evaporator. How making composite with different kind of metal oxide can improve the overall performance. It can also very effectively utilize for micropollutant removal, as well as these emerging these enteric viruses as well. They have shown very good result. The optimization is very precious for these laser-induced graphene, and that we have recently demonstrated, as well as how the groundwater contaminant can be removed. Apart from these electroconductive membrane, we are also trying to do different surface modification. For example, one of the work where these SGO surfaces were used to improve the groundwater contaminant removal, and also how using polymer brushes and we can come up with new anti-fouling surfaces to control biofouling. From the IIT Bombay, we filed several patents and several are also in the pipeline. And the overall objective of our lab is to come for the low-cost surfaces and membranes for desalination and wastewater treatment. So finally, I want to acknowledge the students, my institute, and Indian collaborators, international collaborators from Rice University and Ben Gurion University, the funding agencies, and also IIT Roorkee and Professor Dekha team to giving me the opportunity to talk about my work. These are some of the students' work what I have shown you here. And also, like we recently got a Center of Excellence from DST for a membrane technology, where the overall mandate is how we can collaborate at a national level and come up with cutting edge technologies which can help our in-house membrane-based facility, and also train next generation to come up for new generation membranes and upscale that process indigenously. So thank you.
Thank you, Professor Swatantra, for an excellent presentation.
Thank you, Professor.
And it has really been wonderful to listen to you, various kinds of innovative improvisations which you have done, employing graphene laser, and then how exactly you have tried to modify the surfaces, bring in various kinds of applications. I think only thing is that maybe for a couple of the innovations which you have done, maybe their field trials, further field trials, or further commercial scale applications you might be planning in near future. And we hope and we pray that all those things come good to you and they are successful.
Yeah.
So also congratulations for getting the Center of Excellence, and we feel that you will be working very well, and then just find time to come over sometimes and keep having collaboration with us. So thank you very much once again. Please put your hands together. Thank you very, very much.
Thank you.
And if anyone has any question from the audience at this stage, yeah, maybe it is lunchtime.